All right, thanks very much for the introduction, Elder, and hello to everyone. Good morning. I'm very honored to be a featured guest of the premiere of your new format of your business-focused tech talks. My name is what I would like to talk about today is seen here on the screen. Automation of machine learning. Let the machine do the hard work. My name is Sascha Schubert. I've been working in the area of analytical predictions or predictive analytics, data mining for a long time. I've been with SAS for more than 20 years, always in the area of analytics and predictive modeling. Worked in different roles at SAS. With customers across different branches, different industries, and finance, telecommunication, government, but also in product strategy roles, so helping our R&D department to develop the models and stay up to date on the market with the tools, analytical tools that we provide. And currently, I'm a leader. I lead a team of data scientists in an international team. These guys are located in different countries in Europe. I'm actually located in Heidelberg in Germany, and my team members were located in Italy, in Belgium, and in Finland. And they help our customers to design solutions using the analytical tools of SAS and helping them to use analytics, predictive modeling, artificial intelligence, machine learning, all these things, and put it together to solve business problems and help them to automate processes in their business. I also put down a link here to my LinkedIn profile. So if you want to connect with me on LinkedIn, feel free. You can also get more information about myself on LinkedIn, and always feel free to reach out if you have questions or want to discuss certain things. What I would like to talk about today are these 4 topics. I want to talk a little bit about automation of machine learning, what it actually means, where it's coming from, why we think it's important and will help data scientists in their job to produce machine learning models that help organizations to make smarter decisions in their business and automate decision making. I want to talk about the key steps of machine learning pipelines, what you can automate, how things can be automated, what the approaches are, how it helps to create better models faster. But then I also want to bring in maybe a slightly other focus of that topic. When we talk about machine learning, we often and mostly talk about the development of the models. Really, what is the best way to produce a stable, accurate model that can really be used to make automated decisions in organizations for many different types of business problems. But there's also the other side of the coin, obviously, that once you have the model, how can you integrate that model into your business processes? How can you make the model productive and use the model in automating decision making, in making business processes smarter and more intelligent? And how can you make sure that the models that you are using in different business processes, that they are staying up to date and they are always as accurate as they can be, using the latest data and making accurate decisions? And at the end, as Ella pointed out, we'll have enough time for question and answers, and maybe even kind of a two-sided discussion on the topic. So automation of machine learning, when you ask people about automation, they often think about the use of intelligence or artificial intelligence in their daily life, and there's many different areas where this is already happening in our really daily use of different devices or different processes. So one example might be the digital assistants that we use. So the Siri on your phone, or the Amazon box that you have at your home that you communicate with and that provide services to you. Obviously, these devices need to be able to take the data, so the spoken language in the case of a digital assistant, and understand it, turn it into an action, use a model to provide the service that you might be asking for, and act on that process. And there's so many different areas in our life where we already kind of use these kind of automated processes without even thinking about it. Obviously, you know, your GPS system, automated marketplaces, online shopping, but also in businesses. There's an example here at the top left where artificial intelligence, computer vision is used to automatically control the manufacturing process, the quality of the manufacturing process, and identify issues and problems with that process, and maybe even take automated action if an issue has been identified and a solution, an automated solution, can be applied to that issue. On the top right hand side, it's again, it's kind of monitoring certain issues here, kind of a power line, and they're using drones and see if the trees that are growing near to that power line maybe are interfering with the line, and there needs to be taken some action in order to fix the problems. And obviously another one that we all know is self-driving cars. Again, it's automating a process that has been manual. So usually humans drive the car, and using artificial intelligence to automate that process and let the car drive by itself by identifying objects on the street and taking actions to avoid these objects and follow the flow on the street. But when you dive a little bit deeper into that process, obviously there is kind of on the left-hand side and maybe a traditional process where that creates data, and with the digitalization of our world, more and more processes create more and more digital data. So using sensors, for instance, as you've seen maybe in the previous slide with that production process, they have cameras everywhere, and these cameras are monitoring the process, and these cameras are providing data that we can use to build models using artificial intelligence and machine learning. And these models extract insights from the data, and that insight can be used to identify issues, to predict if a certain event is occurring or has occurred, and then use that output of a model to make decisions in an automated process. And I just talked about the right-hand side, that automated process that is all around us, and is kind of, that's a area that is growing very, very fast. But there's also a lot of automation that can happen in the box of artificial intelligence and machine learning. And that's what I want to talk about today. That box, what needs to be done within that box to create stable, robust, and accurate models as fast as possible, but also with a high degree of confidence that these models can be used to make automated decisions. Because if we rely on machines to make decisions, obviously we want to make sure that the results, the answers that these models provide really are the right answers and the best answers that we can get. So automated machine learning, as I said, I want to talk about automating machine learning pipelines. And this has been kind of tagged as one of the topics or areas to watch by Forbes in 2018. And here's I put down a link here to an article on the Forbes website that you can read if you're interested in that topic, where they talk about what a machine learning workflow, or we call it sometimes machine learning pipelines. And the box that I just showed in the previous slide is broken down into different steps that a person, a data scientist, usually needs to go through to achieve or to turn data into predictions, into insights that can be used for automated decision making. So you have the box like the step of data exploration, and if get your data, access your data, and then start to understand your data. Is that data something that has the potential, that has the power to be used to understand relationships that help us to make predictions? Then usually the data cannot be used as is for modeling purposes, so we need to prepare the data somehow. We need to identify drivers, input features for the model. We need to see if the input data is clean enough to be used for modeling, if there's any issues that might interfere with the accuracy and the power of the model predictions. Feature engineering is often required in order to turn the raw data into a format that is optimal for building the model, is optimal for developing the model in a way that it can be used for predictions. Model selection, which algorithm do we want to use? Which algorithm is appropriate for that specific type of business problem that we want to tackle with that machine learning model? Might be kind of high level and rather easy. If you kind of have image data, you probably want to use a computer vision model, but then there's different types of algorithms that in the computer vision area that you can choose from. If you want to build a classification model, you want to maybe use the more traditional machine learning algorithms, such as decision trees or gradient boosting or neural networks. And often you might want to have different algorithms compete against each other and see which one works best, and train the models using the input data, and then see which model works best on the data that you have at your hand for that specific business problem. A very important step in that pipeline is the hyperparameter tuning. Hyperparameters are the parameters of the models that you can play with, that you can change and tune in order to increase or maximize the accuracy of your model. And obviously different modeling algorithms have different types of hyperparameters that you can tune. And then in the end, bring it all together and create a model that can be used for predictions. And so usually data scientists used to go through this process in a manual way, step by step. And obviously that's not kind of a linear flow. Often there's kind of an iteration that you have to go back maybe to previous steps and change things, and then do the downstream steps again. So it's kind of an often tedious and manual process to go through this pipeline, create this pipeline, and come up with a model that you have trust and confidence in. And the idea of auto machine learning now is how much of this process can we automate in a way that we have an intelligent process here for the different steps that makes this process faster and, if possible, even more accurate. And that will be kind of the main part of my presentation now. So let's have a look into data pre-processing, what can be done. And the goal here for data pre-processing is to generate high quality input features for your models. So first step might be to pre-screen the input to determine the characteristics. So do you have, what kind of variables do you have? Are these kind of nominal variables or interval variables? How many levels would you have in one of the categorical or nominal variables? Some types of modeling algorithms can't really deal very well with high cardinality and categorical variables that have a very large number of levels. So as a data scientist, you might want to know about that and have different strategies to deal with variables that have a high cardinality. Do you have any missing values in your data? And if yes, what's the percentage of missing values in certain features, and would that interfere with the potential of that feature to be used as an input for your model development? If you have a variable that has 80% missing values, is this really useful as a feature or not? And then your raw variables, would you want to use them as raw variables in your model development, or would you want to transform them? what is the best transformation for your variables in relation to what you're trying to predict. In relation, if your target is kind of maybe a classification target, a binary target, or a nominal target, or if it's an interval target. Can you automatically apply the best transformation and create maybe new features? Do you want to use your original features in conjunction with the new features that you're creating, or do you want to kind of reject certain raw data? There's a lot of questions that can be asked and can be addressed already in the data pre-processing stage. On one hand side, to inform the data scientist about the characteristics and the data quality of the input features, and then also make suggestions and provide ways to the data scientist of handling those issues that have been found in the data. And that might be kind of the next step in your machine learning pipeline. So automated feature generation, now that we know there's certain quality issues, there's certain issues with the statistical characteristics of our input features, can we fix that? Can we deal with that and maybe generate features that have a higher potential to provide predictive power to my model? So I listed a few things that can be addressed and are addressed in auto machine learning pipelines in the data preparation step. High cardinality, for instance, mentioned that. So if you have a variable that has a lot of levels, is there a way to identify natural groups in that variable and combine certain levels into groups without losing predictive power in that feature? And can that be done automatically? Is there a problem with the distribution, the shape of the distribution of these input features? And can we fix that? Can we transform the variable to maximize normality, which is or might be a prerequisite for some of the modeling algorithms that we might want to use? Missing values is an interesting one. Obviously, there might be kind of a decision to say, okay, this feature has too many missing values. We can't use that. It's not enough information in that feature. But if you have missing values and you want to use that feature, can we look at that feature and see if the missing values are missing for a reason? And that's what we mean by identify patterns of missingness. Is the missingness random, or is there maybe even predictive power in the pattern of missing values? Are the values missing for a reason in that case? Maybe some type of information is not provided easily by your subjects that you're using in your data. If your customers, if you use customer data, for instance, some of the information they don't want to provide that easily if you have a survey or if you have a certain demographic information on your customers. So is there a pattern in the feature, the pattern of missing values that maybe can be used for predictions? Outliers, obviously, is the outlier an error? Is it really an extreme value that should be used in the prediction? Collinearity is kind of an issue that often arises in data sets with a lot of variables, because many variables that you maybe have in your data sets can be related to each other. And collinearity kind of addresses that issue to identify dependencies between features. And can we select maybe a combination of features, or can we select one single feature that best represents all these dependent features that are linked to that specific feature? And maybe also automatically detect interactions. So not just the first degree of your raw data, but maybe kind of first, second, and third degree interactions, and which interactions should be used as input features in your model. So there's a lot of things that you can address in the automated feature generation, and obviously there's a challenge of during the input screening to define which features should be transformed based on that data quality thresholds or data based on statistical characteristics. And you might need policies implemented that identify certain issues that then lead to using that feature in a feature generation step, or in a automated feature transformation step. And then obviously there's a potential to create a lot of new variables if you address all these issues that I have outlined here, and maybe even more. So what is the best way of defining which new features should become part of your modeling? And that can all be addressed with policies, with automated statistical procedures that help you to identify variables to subject to automated feature cleaning or feature generation, and then also select the ones that have the highest power to be good predictors, good drivers in your model that you want to train. Another way, and I kind of briefly mentioned that already, is automated feature transformation to combine raw variables. That's often used in automated machine learning. So rather than using kind of original raw data that might be linked to each other or might be correlated to each other, use feature transformation algorithms that are based on single value decomposition or principal component analysis to combine these variables and create a new feature that has kind of the input of all these interlinked variables, but kind of lowers the dimension. And there's also kind of a new way of creating that kind of low dimensional feature space, so-called autoencoders. With principal component analysis and single value decomposition, you can create a linear relationship, linear transformation of your raw variables into new feature components. With the autoencoder, the nice thing is you can also include nonlinear relationships. So that's kind of a way of combining the different raw data that are linked to each other in a nonlinear way, and lower the dimensional space of input features at the same time. And I'm not going to go into detail here, but there's a lot of literature out there on autoencoders and how that would work to compress your raw data basically into a smaller number of vectors, feature vectors that you could use instead as input for your model. And then the next step in your pipeline might be automated data exploration. So you've got all your features that you have cleaned and transformed and generated, and how are they related to your target? Can you get a kind of quick view of how strong the relationship is for the different features that you use in your model? And again, there's kind of a way of automating that. And when I say automating, I mean there's one way of running the analysis when you automate this, but the other thing is to kind of automate the results that are presented to make it easier to understand what the automated analysis has uncovered. And here's kind of an example of a report that can be created by a push of a button, for instance, in an automated system, and it provides you insights into the relationship of your input features to your target. And it's an interactive report, so it's easy for the user, for the data scientist, and maybe also the business analyst here to identify and understand these relationships. And on top of the graphs that here to see and to explore, we also can provide kind of a description in plain language where we use artificial intelligence, in this case natural language generation, to provide a description of the results in plain language. Again, makes it easier to understand, makes it easier to understand the relationships, to identify the strong relationships, and maybe see which relationships or which variables should not be used in my modeling approach. So once I've prepared my data, I want to maybe start looking into model tournaments. And model tournaments is what we call the competition of different modeling algorithms against each other in an automated way. And You could use automated static templates. In this case, you have your analytical base table. This is the kind of final product of your data preparation steps, where you have your new features, your cleaned features. You have a set of hyperparameters that you identify for each model, and you have your assessment metrics. So what describes a good model versus a bad model? How do you define that? And then you run your models with automated model templates. And you can even apply auto-tuning. I will talk about auto-tuning a little bit more in a second. And you end up with a champion model. So out of this automated model competition comes a model that, based on your assessment metrics, has been identified as the best performing model. And again, that can all be an automated process, and makes it very easy, very simple to run, and makes it also easy to understand the end results. And you can even take it a step forward. Instead of using automated static model templates, you can use automated dynamic model searches, something that we call model composing. So rather than looking at each model independently with a set of hyperparameters, we're looking at kind of the models across the models and identify the best settings of parameters across different modeling algorithm approaches, basically, and go one level deeper to identify hidden structures in the data, maybe even better, and create a more accurate model. And again, this can be an automated approach, but rather than kind of having a static template of hyperparameters that you use a dynamic search for models that uses optimization techniques and auto-tuning techniques to come up with the best model automatically. So talked about hyperparameter tuning already a little bit. So what are the hyperparameters? Everybody who's kind of a data scientist or is working in that area of building predictive models knows about hyperparameters. These are the settings of models, and with the dawn, or kind of the new wave of artificial intelligence and neural networks, the sets of hyperparameters that you have to tune a model has become more and more complex. If you kind of compare the number of hyperparameters that you have in a decision tree compared to maybe a recurrent neural network, that's kind of a different level, really, what you have in a recurrent neural network in terms of the number of hyperparameters that you can or maybe have to tune. And I sometimes compare that, like building a machine learning model based on a decidual or logistic regression was a little bit like driving a car. So you have in your car you have certain number of instruments. You have your speedometer. You have your gauge to how much petrol you have left, and things like that. The temperature of the engine. It's very it's not that many, and it's easy to understand. And then maybe tuning a recurrent neural network can be more like flying a plane, where you have lots and lots of gauges and instruments that you need to be looking at and monitoring at the same time. And so this tuning hyperparameter has become a more complex task with the use of these more complex modeling algorithms like deep neural networks and recurrent neural networks and so on. And there's different approaches to hyperparameter tuning. They basically kind of differ from each other in terms of using a brute force approach on the left-hand side, where you have a kind of a grid search. You identify certain combinations of hyperparameters, and then you check these combinations step by step in an exhaustive loop and identify the one that works best. And obviously you can miss with that. If you imagine how many hyperparameters you can have and how many combinations can come out of this large number of hyperparameters, all you can work with is a pretty coarse grid that you can search, and you can miss the area where your combination of hyperparameters produces the optimal model very easily. The second approach really is random search, where you have kind of a random approach, and so you select the combination of hyperparameter settings in a random way. And it turned out that the random search often is more successful in finding the optimal model than the standard grid. But obviously, a combination of those two might be the optimal approach, and that's what it's called the Latin hypercube, where you have kind of a systematic variation of each hyperparameter, but then you use a random selection of the combinations. And with that, you can then use optimization techniques to run through these random combinations of hyperparameter settings and find the optimal model as quickly as possible. And that's what's shown here on the slide, where this approach is used, and you run through different iterations. You create populations for your hyperparameter settings, and then you train models. You train your model and you evaluate your model on an holdout data set, maybe a validation set or a cross-validation set. And then you run through this loop in an optimized way, and you use genetic algorithms to slightly, you identify an area that has the potential of creating a good model, and then you vary within that area with genetic algorithms. You vary the hyperparameter settings to see if you have a positive outcome in terms of increasing the accuracy of the model or not. And with that, you can very easily and optimally loop through that process. And then you have certain constraints, how long you want to, how many iterations you have, how long you want to run this process to stop the process at a certain time and identify the model that works best. And that's an automated process, again, that can be used to easily and quickly find the best model with a very large set of potential hyperparameters. Another area that is interesting for automating machine learning is really the automated model documentation. So far, we've talked about automating the model pipeline, but the result at the end might be a model that you can use for predictions. But on the other hand, you might also need to produce documentation of the model, or you need to produce reports on your model that can be shared with other users that might not be that deep into the analytics or the data science that you use to build the model. And with that, you can easily create automatically reports that help other users to understand how the model was built, what the model actually presents, and how the model works. And that's as important in our understanding in order to really establish the predictive model based automated decision making in organizations, that the users that are using the results of the models understand how these results are created. And at the end, you can bring it all together and automate machine learning pipelines. So just a push of a button, basically, and bring all these things that I talked about together and run this process in an optimized way to create a model that is documented and ready to deploy. And by deploy, we mean ready to be put in production and used for automated decision making. So I have a little example here where an application, very kind of simple application, has been built to actually build that machine learning pipeline automatically. So you give the project a name, you identify a data source, you identify a goal. So in this case, we want to kind of look at child security data and identify the risk if child security is under threat or not, if certain action needs to be taken. And then you click on a button to build the model, and all these steps that I talked about, that I just outlined, the data pre-processing, the feature generation, the feature cleaning, the model competition, model search, all this is done automatically, and you come up with a report on the model that has been built. The champion is a gradient boosting in this case. We have a misclassification rate of about 9%. We get insight into the model. But at the same time now, this is not a black box. You can now drill down and actually open that process and look at the pipeline, and as a data scientist may manually kind of go in and customize certain steps in that pipeline. So in this case, I showed that you can run this as a black box, and then you can open the black box to understand what's going on. But at the same time, you might also need to provide more transparency to the models in terms of what is actually driving the model. What are the strong predictors in the model? How stable is the model? What about certain predictions? How are they actually arrived? If I kind of make a decision, yes or no, how strong is the yes? And what are the drivers for that specific yes? So if I make, if I give a credit to a person, I might have to defend that decision if that person complains that the credit was not granted. So with that specific prediction, what were the drivers for that specific prediction? And then also maybe wrap all this up with terms that a business user, so a person who grants a credit usually is not a data scientist, but it's a business person in the organization. Can we wrap all this information into language that this person can understand? And can we use automation to provide that description in a language that this person understands? So here's all about making the black box, open the black box, making the black box transparent, and provide information to a business user so that they can understand how the model works and how the results are achieved. So in my view, in our view, the formula for success are these in terms of using automation for machine learning are these three components. One is speed, one is automation for speed to make the process faster and automate repetitive tasks. The second ingredient is intelligence. So not only automation, but make the process intelligence to be able to identify the best route in the process, the best road to take to arrive at the best possible outcome. And then the third component is transparency to make the black box, open the black box, make it transparent, and help users to understand how these models work that are used to kind of make decisions in the business process. Whereas AutoML headed, from my point of view, it's headed into providing more and more intelligence to auto machine learning, maybe even integrate artificial intelligence more to identify the best possible route of within the process. There's many different ways you could take. So what's the best way? What's the best the way with the potential best outcome? Explainability. There's explainability in terms of understanding, but there's also explainability in terms of ethical. So what data is used? What about data privacy? What about using the results in a way that does not discriminate the recipient of that result, and make it editable? So make it not only understand what's happening in the black box, but being able to go into the black box and change and customize things that need to be changed. And then flexibility, cater to different levels of users with guidance, with widgets, but also with graphical user interfaces, and maybe and also with programming environments and APIs to be able to help data scientists to integrate automated steps into their own pipelines and create their own applications that use maybe different steps of the pipeline or all the steps. And there's one other thing I briefly want to touch on. We talked about the model development here and the different steps of the pipeline to create a model. But the data and the model does not change the organization. It's really the decisions that change the organization. So as long as you don't use the model in production, as long as your model is not used to make decisions in your organizations, the model does not create value. And that's why we have created an analytical lifecycle process that addresses the whole end-to-end process, not only the model development, which we call analytical discovery in this case, but also a step of how do you bring models into production? How do you make that fast, easy, and efficient? And then how do you use the models in business applications? How do you make decisions? and then also have a feedback loop at the end that enables you to monitor the results to identify if the model is creating valuable decisions, and maybe if the model is degrading over time. If you have a model in production in use for a certain time, the model might create less accurate predictions over time. So when is the time to go in and retrain the model, refresh the model, and go through that loop again? So based on that, there's a lot of automation hotspots that can be applied to the model deployment part of the analytical lifecycle. And I just put a list down here: automated model deployment, automated model integration with decision flows, automated model governance, automated model retraining, automated model lifecycle workflow. So these things can all be automated to bring a model into production, to use a model in production, and to identify when a model needs to be retrained. And bringing all this together, you're not talking now about automation of machine learning model development, but automation of the whole machine learning life cycle that again brings speed, productivity, accuracy, and transparency to that process. And why is this important? Because it's all about the value of analytics. So if you look at that graph here, obviously there's a time component to developing a model, and you only start generating value with your model when you bring it into production. So the longer it takes to develop the model, the more time elapses and the more opportunity is missed to use that model for better decision making. And then when you have the model in production, if you don't manage the model, if you don't monitor it, there's decaying value. And you want to really shorten the time to model deployment, make that process as efficient and as fast as possible. And then you want to maximize the value of the model in production. So want to make sure that you identify when the model needs to be retrained and have a good and constant view on the value that is produced through the decision making by the model. And we call this model ops a framework. So the model ops is a framework that helps organization to operationalize the analytics as quickly as possible, to facilitate the collaboration between different functions. So the people that develop the model, the people that provide the data, the people that put the models in productions, the people that use the model in the business process, bring all these different user personas together in an organization to work inside that analytical lifecycle process as efficiently as possible. And then scale the use of predictive analytics for real-time decisioning. So if you think about the many different applications you might have in your organizations for machine learning, you need to maybe produce a lot of models quickly and also be able to manage these models in production. If you have more than one, if you have maybe dozens or even hundreds of models in production, you need to have a framework that enables you to do that easily. And so you can automate that in many aspects, as I shown before of that too. Here's an example maybe of a model ops automation step through pipelines where the quality of the model is assessed automatically. So there's a pipeline that has been created, and the data scientist creates a model, and then the model is registered into a pool, a repository of models. And once that is done, kind of a quality assurance process kicks in, and that quality assurance process assesses or evaluates if the model that has been created by the data scientist is of a certain level of quality, so it can be, or it has the potential to be deployed into production. And again, there's an output provided that then kind of triggers the next step. Once the model has the quality is good enough, let's trigger the next step of deploying this model in production. So again, an automated step, but not on the model development side, but on the model deployment side. And then here it's kind of just an architecture, kind of a process flow diagram of bringing all these things together into kind of an automated, well-managed and governed framework of the analytic lifecycle, where all different personas and different areas work together and automate all the steps to basically produce a machine learning model factory. And so I've got a few links in here that you can look at in the handouts, where you get more information on automation and things that we can do in that area. And with that, I'd like to hand it over to Elda again to open the question and answer session.
So, Sascha, thank you very much for the great overview. And I think that was a great, very packed presentation where a lot of high-level details were mentioned, and also in some places very detailed. And I can see from the chat that we received 14 questions, and I'm afraid that we won't be able to answer all of them. So feel free to stay. And it can be seen that we have also people who have experience with automated machine learning, and I can even see some discussions there. So I will start with the questions, and we have a lot of questions from mostly like from 2 or 3 webinar participants. Many questions from Welderufel, whom I know, who is a very active community member. So hi, and Welderufel, and thanks for your questions. And I will ask them just randomly to be fair. Yeah. So a very interesting question from Tibe Jyoti. So, Sascha, you talked about generating new features from the current features. If so, the question is is it possible to generate a different set of features who are perfectly orthogonal, so null correlation? In mathematics, such renormalization are called Gram-Schmidt process. So I will basically read questions because I'm just afraid to lose some details. Yeah. So, Sascha.
So yeah, so what I understood is if you can create new features that are uncorrelated and orthogonal to each other, and obviously that's possible with the with the autoencoder and also with the principal component analysis. That's what can be. Obviously you can use any other techniques and our techniques. Our approach basically is that we provide a certain number of techniques that you can use out of the box as in a graphical user interface or through APIs in a programming way, and you can always add your own techniques or algorithms to that. So use the ones that are provided out of the box and combine them or extend them with your own techniques that you want to integrate into that process.
So thanks. The next question from Welderufel. One issue of ethics comes from the lack of diversity in data representation and preprocessing. For example, opinions expressed in data labeling. And Welderufel is wondering, does not automated machine learning create even more challenges to an already complicated process?
Obviously, I mean, you always have to monitor the automation quite closely. That's why I also think, I mean, I heard the term once, automation is the data scientist in a box, and I don't agree fully with that, because I think automation needs to be monitored, and there's certain ways of doing that automatically by providing metrics and reports. And I talked about the automated reports that can be created with even language description, but obviously there needs to be someone who kind of looks at the ethical side of things, and I don't think that can be automated right now. Are we using the right data? Are we compliant with kind of the business philosophy, the business strategy? Are we discriminating people because data is always kind of a snapshot, and it's always kind of it's not the whole truth, right? It's kind of a limited way of what is available to us to build the model, and is that limiting the way the model can actually make predictions? And that's something that needs to be monitored and governed by humans, I'm sure.
So thank you. We are going to the next question from Maxim. Does the automated machine learning take into consideration if the best model will be possible to deploy on customer side, or is it only for prototyping?
That's why I brought in the deployment side in the end, which was a little bit rushed. Sorry about that, but obviously we can have maybe another session that focuses a little bit more on the deployment side. But yes, the models that we have included in our automated machine learning process, they can be deployed on the customer side, and to some extent, I think would even probably fully. You can use automation on that side as well to deploy the model if you want to. I mean, there might be certain checks, human checks, that you need to put in to make sure the model is as ready as the automation would tell you. But then you can automatically deploy these models in real time. That was the last slide that I showed, the architecture. So you can deploy these models automatically in real time, in batch, and as always as streaming, also as streaming applications.
Yeah, thank you. So the question from Zinab: since all these phases are linked and all impact the performance of the final model, it must be time consuming because many combinations must be tried to select the best one.
Yeah, I mean, that depends very much on the data. How big is your data? It depends on the complexity of your modeling algorithm. It depends on how many models you want to test and compete against each other. So you can set constraints, right, in the process. You can say, I want to have X numbers of iterations. I want to have the process not running longer than 15 minutes, an hour, 24 hours, whatever you like, can run it overnight. And obviously, we're also using parallel processing in that case. So if you have an environment in your organization where you have a computer network, a cluster, where computers work in parallel or can work in parallel, we can make use or take advantage of that architecture and run these processes. The model tournament, to some extent, can be independent. So model X can be tested independent of model Y. If you don't want to use the correlated model search, then you can run it on different machines. You can run it on across your cluster, and that obviously speeds up the process as well. So we have included a lot of ways of making that process as fast as possible, but it can be a long process. That's true.
Yeah, I'm afraid we are already out of the time. So the last question, if it's possible, shorter, and then we can continue the Q&A round in Zoom. That was the first question. Robert asked, is there anything special needs to be to consider that the correlations you find in large data sets are not just random when using automated machine learning?
Yeah, obviously there's significance levels that you can set as policies on when a correlation should be considered as significant, and then use that. As again, we're not saying that you should always or only trust the automation. That is a way of speeding up certain steps in your process, or maybe speeding up the whole process. But you should always open the black box and check as a data scientist if the process has run as expected.